So the section on stationary states has a couple of important points. The first one being that the wave function can actually be separated into two different functions. And this hinges on one assumption, as in that the potential that the wave function is in, or the particle that the wave function describes is in, is actually independent of time. So the potential is actually varies only with space and not with time. So this allows you to do the separation of variables, which was described in the textbook, but more importantly, that the spatial portion, the time-dependent portion of the wave function is actually a pretty consistent form, which is just a negative complex exponential, e to the negative I times the energy times time over h bar. So anytime that you can determine the spatial part of the wave function, all you need to do is slap this onto the spatial portion of the wave function, and then you have your full time-dependent wave function here. The second key point from this section is that the magnitude squared of the wave function is going to be equal to just the magnitude squared of the spatial portion. That's because when you do the magnitude squared of the wave function, you take the complex conjugate of the wave function and then you multiply it by the normal form of the wave function. What this does is, since you have the time-dependent form that looks like this, you're going to have a negative exponential that looks like this, and the complex conjugate of that is going to be a positive exponential, and they'll cancel out until you eventually just have just the spatial portion here. The third key point has to deal with the expectation values, which is just a fancy way of just saying the average value. So the average value here in brackets, the average value of some arbitrary measurement q can be expressed as this integral here, which the integral has to deal with the associated operator with that measurable. So every measurable is going to have its associated operator with it. Now that operator acts on the wave function here, and then after that operation is performed, then you multiply it by the complex conjugate of the wave function and then integrate it over time. That's because this is actually equal to the probability density, and then whenever you take the integral, you'll end up finding the probability. So an important key point is that the operators are generally a form of some spatial portion, either momentum or space. This being the one that I'm writing right now being the momentum operator here, which we'll get into later. But as you can see, they're only depending on space or the rate of change of space. So that means when that operator acts on the wave function here, when that operator acts on the time and space dependent form of the wave function, it really only acts on the spatial portion of the wave function here. And then since it's an operator and then the wave function is actually an eigenfunction, it produces eigenvalues, which is, again, another fancy way of saying anytime an operator acts on it, it kind of poops out a constant value, that measurement that you'd actually get, but then the wave function just stays the same. It's a really cool function. So eigenfunctions are able to just not be changed, but they just kind of give you that measurement once they're operated on by the operator. And so since this is a constant, it'll move out of the integral here, and then all that's left is the spatial form of the wave function, magnitude squared, as we described here. The fourth key point of this section has to deal with the associated operators. These are definitely worth memorizing, or at least having down on a little cheat sheet. So the space one is relatively simple. The momentum one was described as earlier. And then the Hamiltonian, which just gives you like the full energy, this one being the kinetic and this one being the potential. And the kinetic can also be described in terms of momentum too. So that can also come up on tests or questions or any other form like that. So the last two key points of this section have to do with the linear combination of eigenstates. So the wave function, since it is a solution to the Schrodinger equation, a differential equation, that means a linear combination of anything else that's also a solution can also be expressed as the wave function here. So you can, just kind of like how you can add up sine waves to make one kind of cool looking function, you can do the same thing with the wave functions, where one state has to deal with associated energy and a position, etc. And then a second one would have a different energy. But then you can do a linear combination of all of those. And then the weight, how much you dial up or down, how much of these functions are represented within the wave function is determined by the constant out in front. So the whole wave function can be expressed as a sum from n equals 1 to infinity. So an infinite number of wave functions times their associated weights, or like you can think of them as kind of like volume dials. The higher, these are going to be just constants that you can dial up or down, and then times their associated time dependence form here, each one having a different energy as well. Now, the probability of doing a measurement and yielding some state n, so that'd be like, what's the probability if we do a measurement and then we just get the first state? That's just the constant out in front magnitude squared. So the probability of getting eigenstate 1, or this state right here, is just the magnitude squared of that constant out in front. And then the probability of getting this state is just the magnitude squared of that one as well. And that also goes with other measurements as well. So if you were asked what is the probability of measuring this energy, that is also the same as saying what's the probability of measuring this state n right here. So what's the probability of measuring energy state E2? That's just also the probability of measuring of it being in the eigenstate right here too. So that would just be the magnitude squared of this state. And so those are some of the key points of this section for stationary state.